we're going to start with a little bit of language. There's a lot of people using four-letter words in science, and that's not allowed, okay? And so what am I talking about? Well, we're talking about this. These are all the four-letter words that people use in science, okay? You use any of those, those are all unscientific terms, especially the first few there, energy, field, charge, wave, time, force. If you use any of those to make your case, to do your dissertation, to make your presentation, you are an irrational individual. You haven't gone through kindergarten physics, okay? And so I'm going to be talking a little bit about this, the fact that a lot of people make their case using these words. And they don't understand that, and the context is the following, that they're using a concept as an object, as a thing. So they're moving the field, vibrating the energy, or transferring it, or lifting the mass. You can't do that in physics. Physics, first and foremost, you need an object. You need a thing. You can't do physics without things. If God wiped out all the things in the universe, left absolutely nothing, whatever nothing is, emptiness, space. If God did that, what's happening? What are you observing? What's taking place? And so you need things. And that's the first rule of physics. Okay? I call it the golden principle. You can't do physics without things. None of the words that you see there represent things. All of these are concepts, and when they're used as things, they are irrational. They're irrational concepts. Okay? So yeah, you can't use any of these words. They're outlawed. They're four-letter words as far as science, physics is concerned. Okay, and we're going to be talking a little bit about that today because we had an individual who clarified what he clarified last week. He clarified it again. And what he doesn't understand is this, that he's using four-letter words. Okay, outlawed in physics. Okay, but let me get to this first comment here. And fellow says, singularity, perfect, nothing. Okay, yeah, absolutely. Then he says, space, something. Okay, quantum wave. Well, for that, you need to define what space is and what wave is. Until we define those terms, we have no idea what you're talking about. Space is nothing, so it's not something, as you say there, okay? So if you believe strongly or you want to propose these terms, no problem, but you have to define them. That way we can follow your presentation. Okay, very simple. Okay, and so let's get to this fellow, and he had written a comment. I analyzed it, and then he came back the following week and said, let me clarify what I said. Okay, and here, just very quickly, I'm just going to point to that center one, the one in green, the green box, electrodynamic forces between electrostatic fields. No, forces cannot be between fields. You can talk about horses being between two cornfields. Yeah, that you can talk about. But you cannot talk in physics about forces, concepts, right? Pull, push, being between two fields, whatever field is. Okay, and so he said, let me clarify for you what I meant. Okay, let's go with the clarification. Okay, here we go. And hello. So here we go. Fellow says, clarifying my clarifications. Okay, and electrodynamic forces between fields. Yeah, I wanted a clarification about that because I don't know what a force is. I don't know what a field is. Maybe he's talking about horses and between fields, cornfields. That I can understand. But forces between just fields, what kind of fields? Okay. And he says, I meant forces experienced by what? Charges. By charges. What is a charge? Within fields. He's using this foul language, these four-letter words that he's bringing in here. We don't know what a charge is. What is charge? What is a field? And he says, charge is moving around them. How does a charge move? I mean, what are you talking about? Credit cards? And he's charging? I don't know. I don't know what he's talking about. What is a charge? Okay. And again, all these words were put into his head, in his mouth, right? By the establishment, by the mathematicians out there who invented these words. Why? Because they could not explain. They could not explain a single phenomenon. And so what they did was they created these concepts and they fed them to us, all of us, including myself, in high school, in college, and so on. And so we just repeat and say, oh, the charge, oh, the field, oh, the energy. No such monsters in physics. And that's where the problem is. What they're doing is treating concepts as physical objects. And this fellow doesn't understand that. And he talks about fields and charges and forces. And so, yeah, all I can do is ask him to define those words so that we can understand, we can follow his presentation, we can understand what he's saying. Okay, so that's the problem. That's the starting point. But he just went on and on, just rattling about a lot of stuff. And it's important to look at his language. I want you to look at his entire language. Just how I think fields and electricity work. Okay, well, we'll find out what a field is, I guess, here. The water pressure analogy, where you have water going through a pipe, right, is not 100% accurate. Okay, it's better to think of waves moving. Waves do not move. Waves do not move because wave is already something in motion. It's like saying running runs or flying flies. You can't run, you can't swim, have swimming. Or jumping. And that's what he said. Waves are moving. Waves are waving. Okay, waves travel. Waves are just electrons changing shape. Well, if they're changing shape, they're in motion anyways. Even if it's a changing shape, you're using the word changing, means there's already motion embodied in the wave. So you can't say waves do this and waves do that because you cannot treat it as a noun. Wave is not a noun for the purposes of physics. In ordinary speech, you can say that. Poetry, whatever, yeah. But in science, you cannot say that a wave does this and a wave does that because you're saying that running does this and jumping does that. Okay? And they absorb or emit photons. No, waves cannot absorb or emit anything, and much less photons, whatever those are. What are photons? I mean, are those verbs as well? I mean, are we talking about a little ball, or are we talking about wave, which is already in motion, field, which is already in motion? So you need to tell us what a photon is. Are you talking about a little, stick, a little ball? What is a photon? Patterns of those shapes changing, okay? Actions define the fields they produce. And again, you can't produce fields, okay, because field is not a physical object. Field is a bunch of numbers, that's all it is. From ground zero, you have all these values, whether you're talking about gravitational field or electric field or magnetic field, it doesn't matter. What you're talking about is values becoming weaker as you get farther and farther away from ground zero. Okay, that's what you're talking about. And it just goes on and on. As he says, when you weigh yourself on a scale, you are pushing the scale and the scale is pushing you. Okay, the ladder upwards, push being that what you experience as weight. Okay, you are pushing down on the scale because Earth and the scale is what? Gravitationally attracting you to it. Yeah, what do you mean by that? How? We need to know the mechanism. That's what we're interested in. That's what physics is about. But to say that gravity pulls on you, yeah, you haven't said anything because what we're trying to figure out what gravity is. And the only way you're going to figure that out is by identifying the invisible, intangible mediators of gravity. Okay? Whether this attraction is from ropes or some other mechanism, I guess, is irrelevant to your weight. Yeah, that's he thinks that's irrelevant. That's the only thing that is important. It's the other way around. Weight is a function of ropes in our model, and the more ropes you have, the more weight you have. How simple it is. Because the closer you are to the object that's pulling you, for example, in this instance, the Earth. So yeah, it's the other way around. That is the only thing that's important. What you're going to say next is not important at all. Whether this attraction is from ropes or some mechanism is relevant, he says. What matters is that you are in contact with a scale and you are being accelerated into it. Due to what? The gravity of something. The gravity of something. Yeah, that's what we want to know. We want to understand what is the gravity of, what is that something? That's the part of physics. And the rest is just nonsense, okay? If you were free falling, the only thing that stopped you from completely weightless is that the atmosphere will slow you down. Yeah, you haven't said much. We know all this. We know that a feather, if you let go of a feather, there's more resistance in the air than if you throw an elephant. No mystery there. So you haven't said anything. What we need to figure out is what's pulling it down or pushing it down. If you like push gravity, no problem. Explain the mechanism. Yeah, it's the part that you omitted that is the important part. Okay, and you can't use those foul words, those four-letter words, to give your presentation. Okay, so here he says wires. Okay, all objects, including metallic wires, consist of atoms. Okay, what is an atom? And he says each atom contains positively charged protons. I don't know what a positively charged anything is. Are you charging your credit card? Is that what you're saying? And an equal number of tiny negatively charged electrons. So I don't know what a positively charged or negatively charged whatever is. But, I illustrated what I think he's saying. He's saying there's a positive ball and a negative ball. Okay? Well, what's the problem with this? Here, I'll show you. It's his next statement. He says, orbiting around the core. Around the core. And what do you mean orbiting? You got to explain the mechanism. Why doesn't the electron bead, that electron that's got the negative sign, carries a negative sign over its head, why doesn't it fly away? What's keeping it there? Why does it orbit? Why does it stay faithful to the proton? That's what you got to tell us. And the fellow tries to get away with what they, taught him, what they learned him, in school, in a monastery, I don't know. And that is that positive attracts negative. Okay, let's even go with that. If positive attracts negative, why doesn't the negative bead fall to the positive proton? That's what you got to explain. Why does it spontaneously fly away, and why does it fall towards the blue ball there? And he just says, no, it's just orbiting. It just stays there close to the proton, rolling around it. And so this is the problem. The problem is that he just says things that he memorized, that they fed him, and he just repeats them. He regurgitates them like, it's self-evident and we know it all. No, we don't know nothing. That's not an atom. What you're talking about is an irrational atom, which is the planetary atom, because Bohr's model does not tell us why the electron bead doesn't fly away or fall to the nucleus. Okay, then he goes into current. He says metals consist of a regular arrangement of densely packed atoms, okay, that have electrons that can freely move between the atoms. Why can they move between the atoms? What's pushing them? What's pulling them? How is it that the electron abandons the atom? We have this center ball, which is the proton. We have the electron bead. What compels it to move out? Are you hitting it with something like a paddle, or what compels it to move? You just state that the electrons move, but that's based on the irrational planetary model. Okay, and so you got to start at the atom first and show us your atom and make it work before you say anything, before you explain anything. And of course, if you got this bead, you cannot explain your atom, let alone electricity, which is based on that model. Okay, so let's get that right. These properties make them good conductors of electricity. Okay, outer electrons in each atom are free to move within the metal lattice. Why? These are just statements. You got to tell us why. What's causing the electron to move? Is something pushing, something pulling? You got to tell us that. Conduction electrons can serve on charge carriers. I don't know what a charge carrier is. As charge carriers, or carrying a current. How do you carry a current? You take a river over your shoulder and you carry the river? Is that what you do? It's all irrational language. All of what comes out of his mouth is just irrational language. It's just words that he learned somewhere at the monastery, and he just regurgitates them. He says, oh, charge carriers, like if you knew like if he knew what he's talking about, let alone whoever listens to him. Metals are conductive because there are many free electrons. Well, they should put them in prison, I guess. Too many free electrons, that's the problem. Get it to your head. Okay, so here we have, he says, with no external electric field applied, okay, whatever that is, whatever a field is, right? These electrons move about randomly due to energy. So we have field and energy, but there is zero current within the metal. Yeah, I assume there's no current. I mean, if there's no river, you have no current. I mean, what is he talking about? What is this field, this energy, this current? These four-letter words. The net force on each charge carrier is nearly zero because what? The field from other charges nearby cancel out. So the fields cancel out, whatever that is, whatever a field is. Okay? We're having a field day here. And the electrons are moving in circles. No, I think it's you who's moving in circles like that dog there, chasing his tail around. Okay? You're moving in circles. Okay, and he continues. He goes with this. He says, as George Gamow wrote in his popular science book 1, 2, 3, Infinity, the metallic substances, see, this is where he gets his information, differ from all other materials by the fact that the outer shells of their atoms are bound. What do you mean the outer shells? Where did the shell come in? All we had in the atom was a little ball and a big ball, a little red ball, negative sign on its hat, and the other positive on its cap in the center. How did we end up with this word shell? Where's the eggshell? I don't see any shell there. And then he continues, he says, rather loosely and often let one of their electrons go free. Yeah, again, Gamow has to tell us what prevents the little electron bead from falling towards the positive nucleus or leaving spontaneously the atom completely. And he continues, says, thus the interior, this is from him now, thus the interior of a metal is filled up with large number of what? Unattached electrons that travel aimlessly around like a crowd of displaced persons. I think it's you who are traveling aimlessly. What do you mean unattached electrons? They weren't attached to begin with. What were they attached with? That's what you got to tell us. And again, this fellow, he just uses words that he doesn't even know what he's saying. What do you mean attached? Attached to what? Is there a string attaching them? No strings attached? I mean, I don't know what he's talking about. And here he continues, says, when a metal wire is subjected to field pressure, well, I don't know, is he talking about a wheat field or maybe a football field? You know, you have these waves in the football field, you know, and so I don't know if there's some pressure there, you know, when you do the wave. Applied on its opposite ends voltage. Yeah, what is this voltage thingy? These free electrons rush in the direction of the field. Why, they're trying to pick up the ball there in the middle of the field? I mean, what do you mean free electrons? What do you mean it's rushing towards the field? Field is a concept. You don't rush towards a concept. You don't rush towards love or, I don't know, grace. Thus forming what we call an electric current. Yeah, I don't know what an electric current is. So you got to tell us what a current is. Current of what? Is it a river, you know? What is this current made of? Is it made out of little balls, electron beads that are just flowing en masse away from their atoms? I mean, all this has to be visual. You have to tell us, you have to show us a picture, a movie, if you're going to talk about, you know, the flowing of what, current? You know, I mean, if I tell you the current of a river, I can illustrate that. I can show you, look, there's a river, it's flowing. We call that a current. Everybody can understand that, okay? Even in ordinary speech, you may even understand it in physics, even though you can't use the word current as a thing, okay? But I can say, well, that's what we mean by current in ordinary speech, because you see all this water flowing. We call that water flowing a current. So what is flowing in the case of electricity? Is it all these electron beads? You know, why are they flowing? What's pulling them? What's pushing them? Why didn't they leave spontaneously before you put the voltage there? All this stuff. What is this voltage? What does it do to the beads? Is it some paddle that hits them and they start moving? Is that how it works? I mean, it's the mechanism that we're interested in physics, not the verbiage. And well, he continues here. A couple more here. It says motion of the charges. Motion of the charge. How can a charge move if a charge is 1 times 10 to the minus 19, 1.6 times 10 to the minus 19 coulombs? That's what a charge is. And he's saying the motion of this number. How can a number move? Coulomb. We're going to move the coulombs. It's still only the order of millimeters, I guess, because like charges repel each other. What do you mean like charges? You mean negative against negative? Why don't they add? Why don't you get more negative? Positive against positive, you get more positive. I don't know. I mean, it's this foul language that this poor fellow uses. And he continues there, the energy of the charges must be traveling. The energy must be traveling. Yeah, I guess. I mean, depends on how high you are, via waves of some sort. And again, he just leaves that all up in the air, like it's some wave of some kind. I don't know, and I don't care. I just want to tell you my theory. Each wave impulse faster than the electrons. I mean, waves can't impulse anything, right? Waves can be guided, no, by current carrying wires, no, by current carrying anything. Wave is not a physical object, okay? And charge densities can act as a medium, absolutely not. Charge is not a medium, okay, and much less a density. Waves can cause field variations, absolutely not. Waves as a concept cannot cause anything in physics, much less a field variation, which is a number in mathematics. They can escape the wires entirely. No, waves cannot escape, especially out of this universe. We call that radiation. What is radiation? An escape wave, which can be in the form of heat. No, heat, radio, and light don't have form. Okay, not those words, at least. So this is the problem. They're poisoned with all this language, and this is the language that they use. This is how they communicate their ideas. This is what they learn, and they just regurgitate it without ever questioning their instructors or teachers, whatever, priests. They never question them. Oh, what do you mean by wave? What do you mean by energy? What do you mean by field? And they never question that. They just say, I'm going to use this word. It's not this word. And the problem with that is that when you come here, and we don't use that foul language. We say, look, this is a horse, and this is a table, and this is a house, and this is a tree. And I think everybody can understand that because I point to them. I say, look, that's a tree, that's a house, that's a table, that's a chair, and so on. So you say, okay, I know what he's talking about. It's that thing that he pointed to. I put a name to the noun that I, pointed to, designated. So now I can say, I'm going to move the tree. Everybody can understand that because I can film it. I can, show you a movie of me moving a tree. And if I tell you that, look, the rock broke the window, hey, I can illustrate that. Here's the rock, here's flying, and it broke the window. Do I need to know how thick the window is? No, I'm just wondering why the glass fell on the floor, why it's all broken in pieces. I'm saying because the theory is that I threw a rock through the window. That's the mechanism. That's how the window broke. But these people say, look, there's a mass, and I threw it so much force, and the energy, hit the window and it broke. And we haven't understood squat because none of that is physics. None of that has anything to do with physics. And these people that can't follow a normal presentation using objects, they say, you're talking kindergarten stuff here. Yeah. This is all physics is kindergarten. You don't need to know any math. You don't need to imagine beyond your wildest dreams. You just visualize or watch the movie, the mechanism. You say, okay, I understand how that happened. And that's the way we have to explain, why a spoon falls downwards. We have a spoon and we have the earth. We know this, or our experience is, right, that this always falls to the ground. And all we have to do is explain it. And for that, you're going to need some object here, either pushing or pulling. But there's no other, as far as I know, there's no other force, right? It's either push or pull. And so you have to identify the invisible mediators, intangible also, right? And once you do that, then you can show the movie, and that's how easy gravity is. And the only reason that we are 10,000 years later, nobody can tell you what gravity is because no one has identified the invisible, intangible mediators. That's the whole issue. Once you identify them, it's kindergarten stuff. It's kindergarten. I mean, really kindergarten. Here's my model. I'm saying it's being pulled. And I always show this, so I'm illustrating it with this. It's not that I'm saying a rubber band is pulling, okay? But if I want to explain pull, very easy. I have a pen here. I put the rubber band, right? And I pull it down. See how easy it is? I can explain pull. If you see it without the rubber band, here I'll do it without the rubber band. You say, oh, how did that happen? That's magic. But if I show you the rubber band, you say, oh, okay, hey, that's so easy. That's kindergarten stuff, So the only difference between these is that you can see the mediator here, you cannot see it here. That's the only difference. And that's what stumped all these researchers. They never realized that there are invisible, intangible mediators, and you're not going to elucidate, you're not going to imagine them or detect them in any way by going to the lab or going to the field and running some kind of experiment. You cannot determine these things or zero in on them through experiments. You cannot go to the lab, you cannot use your hands or your eyes. There's only one way, and that's imagine, visualize. Then you can understand how this universe works. No problem. It's very easy. It's Father Universe and Mother Nature. They never went to school. They never learned math. All they know is they have to push one atom at a time everywhere in the universe. One atom from here to there, then from there, and there to there. And all they do is just move one atom from one place to another throughout the universe. That's how easy it is. That's how easy our universe is. Okay, this fellow did have a good point here, and he said the following, and listen to this. It says, can you explain in detail how various components of a circuit work with ropes and threads? The rope model, and I believe I've explained all of those. I cannot vouch completely, but I think I've explained all of them. And what I've done as a result of this request, I started with a battery today. Okay, about an hour ago, I uploaded a video that was done in 2018. So what I did was I chopped it up, edited it, and I started with the battery. And I'll be going through these in that channel, that series of videos through all the things involving electricity. So all these things I'll be touching upon. I'll just go through my videos and find out which ones I've already covered. And if I haven't covered one, then I will cover it. So I started with battery, and I'll be uploading some of these videos in the coming weeks. Okay, so I will answer his question. I thought it was a good idea to do it anyways, because I've done some of these in the past, and people may wonder, how do you do electricity with the rope model? How do you do light? How do you do gravity? And so it's a fair question, especially for electricity. So I'm going to do just electricity in that channel. Okay, so here we have the problem that I'll have with this gentleman, because he hasn't gone through kindergarten physics. He hasn't learned the scientific method. Okay, he doesn't know what the scientific method is, because none of the words that he used were objects, were nouns, were things for the purposes of physics. And so we have to start here, and this is where he's got to start. He's got to go to kindergarten. Okay, what is science? Rational explanations. In science, we do not describe. In science, we explain. And we're not interested in philosophy in this channel, not very much at least. We're interested in physics. What is physics? Well, first of all, you have to have an object. You have to have a thing. Okay, without a thing, there is nothing. So nothing is happening. Okay, that's the first one. Then what do? We explain causes and mechanisms. And there on the right-hand side, we show the rational scientific method as applied to physics. And we have what is known as the hypothesis, which is not a theory, which is not an explanation. It's not a tentative theory or anything that it means in the religion of mathematics. No, hypothesis is your set of assumptions. And what are the assumptions? You need to have the objects. You need to have your definitions. We cannot communicate without language, what a lot of people call word salad or semantics. And we call them definitions. And then you have to have the initial scene. You have to show us how your film starts, how your explanation starts at a first frame. We need to see that first frame or the first series of frames, so that we get an idea what you're going to explain, right? And so we call it the statement of the facts. And then you move on to the mechanisms and causes. That's the theory, and finally the conclusions. So this fellow has to go through this. He has never seen this, I guess. He's never been to kindergarten physics. He just jumps ahead and say, oh, because a lot of these people, they go to the labs, and they know how to handle a resistor, or they deal with voltmeters, and they measure current, and they work with all this stuff, and they know it like the palm of their hands. But they never understand what's happening at the atomic and subatomic levels. That's where they fail. They have no idea what's going on with carriers and as they're known, atoms, electrons. They don't know what's going on in that invisible world. They never visualize it. They just say, hey, I know that if I put my 2 electrodes here, I measure so much current, so much resistance, so much voltage. That they know by heart. They know how to handle an oscilloscope, voltmeter. They all that stuff they know. They're usually electricians, a lot of these folks. But they know nothing about physics, because physics is none of that. Physics is about explaining the mechanism, especially at the atomic and subatomic level. You have to tell us what the mediator of light is, what the mediator of this so-called field is, what is a field. You have to tell us when you transfer energy, what it is that you transferred. You need to see the picture of that thing that you call energy, and so on down the line. And they're not used to doing that, and that's when they come here and you say, hey, what does the ether look like? Please illustrate it for me. And why are you asking that question? What kind of question is that? What do you mean, what does the ether look like, or what is the ether? Let me tell you my theory. So they skip over the important part, illustrating or defining the ether, and they never do that. They never learn that. That's the first step. And so they jump past the first step, and they want to tell you their theory. They say, let me tell you how this universe works. How can you tell me how this universe works if you don't know what the ether is? And ether is the foundation of your theory. So yeah, the first step is you got to point to the ether. And so we're going to do that in a minute here. We're going to go into what the ether is, or the history of the ether. Okay? So let's move on. I had one more issue here. Let me show you this. So it says, as long as God was a bush or a magician, it was okay for a starting point. Okay? But when we try to explain his actions, also known as miracles, then we run into problems. No kidding. Like making nothing morph into something in 0 time. Right there you see it. First frame in the film, the one on the left, far left, there's nothing. Okay, we'll put black and we'll call that nothing, right? There's nothing there. And suddenly in frame number 1, or number 2, let's call it number 2, we see a little dot. And that could be a singularity, it can be whatever you want it to be, it doesn't matter. Suddenly we went from nothing to something. And God did it in 0 time because it's the next frame in the film. And you can chop the film as much as you want, no matter how much you want to cut it. It doesn't matter. The next frame in the film, you already have something. How did God do it? The mechanism. That's what we want to see. And of course, when they talk about singularities, mathematical physicists, they go in there and they say, look, we can't tell you what happened in frame number 1. We start at frame number 2. No kidding. And yeah, he says, how does it happen? Can that be rationally explained? Absolutely not. Right? Not even God can explain that. Okay? And yeah, then from there we have the universe, right? And so yes, this is the problem. The problem is that you need to define the language, and you need to show us the pictures of the objects that underlie your theory, your dissertation. If you cannot do that, you are not a scientist.